This is a lecture on directional derivatives and also some more information on the gradient vector. The partial derivatives showed the derivative only in the direction of the coordinate axis, only along the x direction or along the y direction or along the z direction. Of course, you would like to find the derivative in an arbitrary direction. To do that, you use the gradient vector. So let's say that u equals ay plus bj is a unit vector in any arbitrary direction. Then to find the gradient, well, let's say it's also a unit vector, right? Then to find the derivative in that direction, you project the gradient vector, okay, onto the direction u. So here's your gradient vector, the partial with respect to x in the I direction plus the partial with respect to y in the j direction, and you take the dot product of that with a unit vector in the arbitrary direction, and that will give you the derivative in an arbitrary direction. Okay, in this drawing we see the gradient vector as I plus 2j, right? You're not seeing the partial with respect to x and the partial with respect to y. Those have the value of 1 at this point, evaluated at the point 2 and 0, and the partial with respect to y, evaluate at the point 2, 0, has the value of 2. So we're seeing the gradient vector at a particular point for this function. Right, then we have another arbitrary direction, which was denoted u. This is a unit vector, okay, and it's pointing in this direction. Now to find the derivative along that direction, you take the gradient vector and you take the dot product of that with this unit vector u in the direction you're interested in. Here's an example. You get actually -1. So along this direction the vector is like it's going in that direction. It's very small. Now here we're going to derive those results that I said in the first lecture about the relationship between the change, the maximum change and minimum change, and the direction of no change for the function itself and the direction of the gradient. So let's look at any arbitrary unit vector u, and if we're taking the dot product of the gradient with u, we could write it in terms of the magnitude of the gradient times the cosine of the angle between them. Recall that for dot product, let's say I have two vectors v dot u. That could be written as the magnitude of v times the magnitude of u times the cosine of theta, where theta is the angle between v and u. So in this case, phi is the angle between u and the gradient, and because it's a unit vector, its magnitude is 1. So now look at how does cosine phi behave, right? If it's 0, that means that u is parallel to the gradient of f, and that would mean that this result would be a maximum because cosine can't be any bigger than 1, and at that point it would be 1. If you look 180 degrees off from that direction, so now u is anti-parallel to the gradient of f, then it would be a minimum, because at that point cosine of phi is going to be -1 at its minimum, and here cosine of phi is equal to 1, that's its maximum, and at plus and minus pi over 2, cosine of phi is going to be 0, and that's where you get these results here. There's your maximum, your 0, and your minimum. So if you look in the direction of the gradient, you will find that the rate of change there is maximum. If you look in the direction anti-parallel to the direction of the gradient, you'll find that the rate of change is minimum, and if you look perpendicular, you will find the rate of change is 0. This is a picture from one of the textbooks, and it's very hard to understand because of the 3D effect of it. But what we have here is the gradient. Look at the projection down into the plane. Here's a gradient, is I plus j, 1 in the I direction plus 1 in the j direction. Right. In this direction, the change, this particular bowl, is increasing fastest if you go in the direction of the gradient. So it's getting bigger here, but I think this is a 3D artifact. If you go in that direction, it's getting bigger fastest. If you go in this direction, it's getting smaller, and that's the rate of change would be smallest, to be decreasing maximally in this direction. And perpendicular, there's no change. If you stay along this line perpendicular to the gradient, you wouldn't have any change in your, shall we say, elevation along this bowl. This effect is easier to see when you look on the contour lines. If these are contour lines with respect to some elevation, and here's 300, 200, 100, so this, let's say this is feet above sea level, the direction of the gradient here will take you in the direction of maximum ascent. This would be the steepest ascent up this hill. If you look in this direction, from this point, going opposite the gradient would be the steepest or the fastest descent down the hill. If you're perpendicular, you will be on a no change, a line of no change of elevation. Of course, you see these are going to change at every point because this isn't like a perfect circle or anything. This is has some structure to it. So if you're thinking in terms of water, and you're sitting at this point, this is the direction that the water is going to roll down the hill. Here it's going to roll in this direction. Here it's going to be rolling in this direction. Here it will be rolling in that direction. So water takes the easiest path down, or the fastest path down the hill. So your gradient would be in this direction, but your water would roll in that direction. And if you stayed on this path, perpendicular to all the gradients that occur, you stayed on this path, you would not have any change in elevation. If you're thinking about temperature, then the temperature is increasing most rapidly in the direction of the gradient. But notice that heat will flow from hot to cold. So the direction of heat flow, sort of like the direction of water flowing, would be anti-parallel to the direction of the gradient. Here is the equation for heat flux. Q equals minus K times the gradient of the temperature. So there you see some constant times the negative of the gradient, anti-parallel to the gradient. Now, any line perpendicular to the gradient is an isotherm. Remember that iso means the same, and so an isotherm would be a contour line of the same temperature. If you're more familiar with electricity, the electric field is the gradient of the voltage. So the electric field lines would be perpendicular to lines of constant voltage. So here you see this would be, if this line means 3 volts, this line means 2 volts, then when you draw the electric field lines, they will always be perpendicular to them, because perpendicular to this line of 3 volts, this line of constant voltage. Here the voltage is 2 volts right along this path here, and the electric field will be at right angles to that. Down here, it's a little bit flatter surface, and you see that the electric vector has changed. If you think in terms of a point source, then the lines of constant voltage are circles. So these dashed lines are constant voltage, just like you had constant temperature or constant elevation. And the well, there's a negative associated with this, don't worry about that. And the gradient is perpendicular to those lines. So the gradient will look like spokes here, and the because the lines are circular. The lines of constant voltage are circular.